there that I found really interesting. It kind of goes through it and starts with TLS there in the middle, and then you can see right here it says green is recommended, blue is standard, orange is like deprecated, yeah, and red is dangerous. And so you can kind of see as it goes through the different mappings between them. So TLS, the recommended is DNG, maybe element, and then from there where you share key, and you can kind of see each of the different pieces, and then it even goes and breaks down. So we move in a little closer because it's hard to see from back there. It talks about each one. So here's a little bit of information about RSA. Here it tells export cyberspace has been built as dangerous and shouldn't be used. Arson core, symmetric encryption should not be used. And so it's a really good infographic because it kind of goes through each of the different technologies, each of the different encryption algorithms, and kind of comes and tells you why it's good, why it's bad, what you should and shouldn't be using. It's not. I can. Yeah, this was one of our web admins actually sent this to me the other day, and I was like, "Ooh, that's really interesting." I found it to be really cool graphics. Picture of it. Yeah, it's just a mind map on all the different variations on TLS and what's considered good and what's considered bad. All right, let's see if we can get out of this. And you want to hear it? Yeah, no problem. Isn't that neat? Yeah. You can tell it's done not by somebody who's a native English speaker because there's a few grammatical mistakes in there, but we'll forgive them because it's really good information. Yeah, right?
One little anecdote about those of you who may be thinking about rolling your own crypto. A really good friend of mine, a guy I used to work with, wanted to go live in the big city in New York. And so he got a job. He's kind of a mathy guy. So he got a job with a company that used to be called Theos. And what they did is they made high performance cryptography implementations. They started out with the Java ME platform and whatnot. And I talked to him a week or two after he got up there, and I said, what do they have you working on? He's like, oh, the first week I went and I implemented RSA. And I was like, wasn't that what you guys do? Is the company done now? He's like, no, that's what they make everybody do in their first week, is you have to write an implementation of RSA, and then everybody sits in the conference room and craps all over the implementation you made. So if you're thinking about writing your own crypto, don't, because it's really, really hard and best done by specialists. So we're going to talk about something that I find as a application penetration tester, both web applications, but also thick client applications and mobile applications especially. This is a topic that I find to be very interesting, and that is situations where you have missing access control for different functions in the application. There we go. And we'll talk about it again, kind of specifically for web applications, but I'll also give some thick client and mobile application examples as well, because I think they're really germane. And this is a problem that we see, like always, kind of reoccurring or resurging. And so the problem occurs when you have things that users are maybe not supposed to be able to do, right? In order to do this, you need to be logged in. In order to do that, you need to be an administrator, right? So authorization that needs to be applied to parts of the application. And the problem occurs when you don't have actual checks in place to make sure, should this user be able to do this thing in the application. And a lot of times this gets glossed over because when you render like the front end HTML stuff for the application, you wouldn't render links to stuff that the current user should be able to do, right? When you're rendering the page, you say, is the user logged in? If so, render the logged in person menu. Otherwise, render the non-logged in person menu, right? But and so a lot of times this control is handled from a visibility basis. But if an attacker knows where to send the requests, when the request gets there, that request is not going to check and say, well, this is actually an unauthenticated user, and I'm not going to allow them to perform this function. And so this comes down to situations where you aren't checking on the server side, should this request be honored, right? Do I know who this user is, and should this user be able to undertake this function? And as I said, we've seen this evolve over time, and organizations have gotten better at parts of it, but then new technologies have emerged that led to problems. So it used to be that everybody had problems. If you had like an administrative part of your web application, if someone could brute force or just directly surf to /admin, even though they hadn't been logged in, that page would still render for them, right? Because the developers relied on no one's going to come to this URL because I'm not going to provide a link to it. But again, /admin or reports or something like that, that's using security through obscurity to keep people from accessing parts of the application. And security through obscurity, there's certainly value in obscurity. That's why we say don't have verbose error messages, right? You don't need to help attackers. But relying solely on obscurity is a pretty brittle approach to security. So the evolution that we saw in the applications we've tested is, it used to be that no one applied any authorization to accessing sensitive directories in web applications. They finally figured this out. And then everybody started making AJAX web applications. And the main URLs that you could navigate to had authorization applied to them. But all of the AJAX endpoints had no authentication or authorization checking. They were just all exposed. And then people kind of figured that out. And then everybody started building mobile applications, right? And with your mobile application, you can render or not render parts of the user interface based on whatever. But at the end of the day, those are talking back to web services. So we started seeing a lot of web services that were exposed without a requirement for authentication or authorization. And so everybody kind of figures this out with one generation of technology, then something new gets released, or a new approach to this, a new approach to exposing application functionality comes along, and people seem to forget all over again, oh yeah, I need to actually put checks in place to make sure that this request that it's arrived at my doorstep, that I actually want to service this request. So the impact of this is moderate. The flaws are going to allow attackers to access functionality they're not authorized to have access to. And again, administrative functions are oftentimes a key target for this type of attack. And if folks can access administrative functions in your application, that's probably not a good thing. Because they're probably going to be able to do stuff or get information or whatever else it might be that they're not supposed to have access to. So you've got to think about the business value of the administrative functions that are being exposed. Can administrators look at more data than the average users? Can the administrators deal with data integrity, turn accounts on, turn accounts off, do other things that attackers may want to do? And this is also the type of thing where you have potential impact to the reputations if vulnerability became public. If do folks remember when the iPad came out a million years ago, or 8 or 6 or however many it was? But anybody remember that AT&T had a problem where they exposed a web service where if you passed in ICC ID, like the mobile account unique identifier, which is a big scary looking number, if you passed that in, they would return the email address of the user associated with that account. All right. Unfortunately, those IDs, though they look very arcane, there's a much like with credit cards and other things, there's a function you can apply to say, well, this is a valid number, this is not. There's like a checksum. And so, was it Weave, the hacker, whatever, basically just cycled through and pulled out 100,000 email addresses or something like that because this web service was exposed and had no authentication or authorization applied to it. And so you get all kinds of great email addresses that people have fun with, like .mil and other stuff like that, where it's like, oh, look, we've got General's email addresses, because they're signed up for this because AT&T didn't provide proper server-side control of this web service. So there's reputation impact associated with this as well. So the best way to figure out if you have a problem with access control is basically to look at your application and see and understand, first of all, what are all the things that my application will allow you to do, right? What are all the URLs that are exposed? What are all the things that can be passed in? What are all the capabilities that this application has? And even in situations where the user interface may not render access to those, are there actual server-side authentication or authorization checks missing? Can I surf directly to these pages that should be restricted, even though I haven't logged into the application? Or even can I move to these admin pages, even though I'm only logged in as a standard user? And so you want to be checking to see essentially, like, are there actual server-side checks that are being performed? Or am I simply relying on the attacker not knowing where to go to because those parts hadn't been rendered in the user interface? As an aside, actually tomorrow, whatever time it is, I'll be giving a talk looking at attack surface calculation for applications and how you can, like, the value of watching that change over time so you can see as your application grows and changes. So if attack surface stuff is interesting, I'll be showing off some stuff that we've done with that tomorrow at whatever time. So that's my advertisement for tomorrow if you're attending the conference. So, this is the type of thing where you can use a proxy to browse your application while you're logged into the privileged role and see all the different pages that you have access to in that privileged role. Then if you can log out and re-navigate to those pages, then you're probably vulnerable. You can also check the access control implementation in the code, right? If you ask a developer, if you are the developer, ask the question of, like, how do you know? Like, this is a sensitive function that someone has access to. How do you know that this user should actually have access to this stuff? And these are the types of things, whereas before we had talked about situations like vulnerabilities like SQL injection and cross-site scripting, where automation can be really valuable in finding those types of vulnerabilities. That is less the case with these situations, because really you're asking questions about the business logic of the application, right? What should this application let me do? Well, that's going to depend. If I'm in kind of the example of thinking about these that I use a lot is if I'm using a web application exposed by Amazon, and I can go to different URLs to look at order number 1, order number 2, order number 3, right? And I can see all the orders by navigating these URLs. If I'm a customer service representative for Amazon using a customer service representative application, it's probably totally cool, right? This application is one that's supposed to show me all of the orders because I may need to pull up any given customer's order on any given day. But if I'm looking at www.amazon.com, that's probably a bad thing because I should only be able to see the orders that are mine, and those are the only orders that I'm authorized to see. And making those kinds of distinctions is the type of thing that automation and these scanning tools are simply just not able to do, right? They're not able to understand what they're seeing in a given request and response, what that means from a business standpoint. And so testing for these missing function, server-side access controls is the type of thing that has to be done, has to be done manually, right? Or with humans looking at these things. So let's look at one example scenario. If you can force browse to different URLs, and if these URLs should require authentication but don't, then you find yourself in a bad situation. And so if both of these URLs are supposed to have, you're supposed to be logged in. If you can get to either of these URLs in this application without being logged in, that's a bad thing. And maybe if you're logged in, but as a normal user, you should be able to see the first one, but not the second one. If you can log in and look at the second one, that's a problem. And so, again, to be able to make determinations about these things, you have to understand the application, understand what the application is doing from a business standpoint, what's important, what's valuable, And then you have to be able to make a determination. Is this behavior desirable, or is this behavior indicative that we have a situation where we're not properly controlling access to different resources? Another scenario, if you have an application where you pass in an action parameter, I want to create user, I want to update order, I want to do X, Y, Z. If you're passing in this parameter, again, the question is, what are the requirements from an authentication standpoint? Should the user have had to identify themselves to the system before they can do this? And does the specific identity of the user determine whether or not they should be able to do whatever function that might be? You can, test, craft requests to say, I'm a non-logged in user. Can I create an account? Can I change an order? Yes or no? Should I be able to? Should I not be able to? A great, my favorite example of these of missing server-side access controls is we did a security test of a thick client.NET application a while back. It's been a couple years now, but they had this thick client application to be used by customer service representatives, and it called back into a bunch of server-side web calls, probably using SOAP or some other gross thing that .NET wanted to use at that point in time. And what we did is we got the binary for the application. For the thick client application, we had our test account on the services. The first thing we did is we decompiled the .NET application, and it had a class in there called security manager, where if it was given a role, it would say yes or no, should I have this permission, this permission, this permission. We just wrote our own security manager class that just said yes, return true to all those functions. Rebuild the application, fired it up, and all of a sudden we had a God mode console, because this application relied on the user interface of this thick client to perform this access control. The thing was, if I don't render a button that says delete account, they're never going to be able to delete an account. The problem was the way that the system worked was, if it got a request to the delete account web service, it didn't require, I think it required authentication, but it did not require any authorization. So when you had, as long as you could connect to this backend system, you could delete accounts no matter what the permissions of that account should be. And that's the same type of thing that we find now with a lot of mobile applications. You've got these mobile applications that are front ends for some sort of functionality, and they are responsible, or the developers rely on them to provide that access control. Should I render this control or not, right? And when I try to take an action, it is expected that the mobile application is going to craft that request and send it. And so what we see are web services that have only ever seen traffic from an approved mobile client. They've never seen or been exposed to any adversarial traffic. So when you start sending malformed requests, you see all kinds of weird failures. But if you watch some of the traffic go through, if you attach, if you run the traffic through the mobile app, through a proxy, and then out to the application, you can see, here's the request they're sending in, here's the JSON that comes back, and you can start to see, okay, well, the legitimate client is only ever going to request balances from my accounts, right? Because, again, makes requests, it logs in, says, hey, I'm Joe, giving the list of Joe's 4 accounts. Cool. Here's what a request looks like for an account 1, account 2, account 3, account 4. Well, if you start to craft your own request to those web services, the web service assumes my mobile client is never going to make a request for an account that that logged in user shouldn't have access to, and there's no server-side check. But if you bypass the legitimate client and just send a request directly to the web service, because there's no server-side control, it'll send back a balance for any account, any arbitrary account where you know a valid number. So those are the types of situations you need to be concerned about when you're thinking about providing those server-side access controls. Because again, the assumption on the developer's part, and this is borne out through all of the application testing, but the assumption on the developer's part is, I'm only going to see traffic coming in from the client that I created, right? I'm only going to get requests in by someone clicking on a link that I've rendered, and therefore, all these requests, I just need to do what the request told me. Whereas, what you really need to do is understand, hey, this web service exposes sensitive functionality. When I get a request, I need to make a determination. Has this user been successfully authenticated or not? And is that required? Right? There may be web services that don't require authentication. Great. If a web service does require authentication, when you get that request in, ask what user is associated with this web request? What role or roles do they have? And is that sufficient for them to have access to this? And also, as Josh talked about with the insecure direct object reference, from an authorization standpoint, given this user, the data that they're requesting to see or to modify, should that user have the right to, to perform that function on that particular piece of data? Like, as developers, that's what we need to do in order to avoid introducing these types of vulnerabilities. So how do you prevent missing function level access control? This isn't something where if you can create a matrix that shows here are the different functions we have. Here are the roles associated with them. These are the roles that should have access to different functions. Here are any data rules that we need to follow. For example, normal users should only be able to see information for accounts that they have. If you can lay that out as a matrix, then you can start to go in and audit these things, especially if this all comes through one central location. That makes it a little bit easier to go in and audit to say, for a given request, is it being routed appropriately, and do we have the right checks in place to enforce the business rules that that this applies to? And similarly, if you have multi-step processes like workflows and whatnot, again, on the server side, you want to make sure if there are rules that you are expecting to have followed, you need to have checks to follow along and make sure those rules are being appropriately followed. Again, in the Java-specific world, you can control the authentication authorization requirements of URLs in your web application in the web.xml. Java also has the Jazz authentication and authorization service, again, built into the platform. So to recap, these problems occur when you don't have proper checks and controls on the server side to make sure, do I need this request to be authenticated or not? And if I do need the request to be authenticated, with this authenticated request, does this user have the appropriate role, and should they have access to this particular data? Again, this is the type of thing that typically has to be tested for manually. There's some things that you can do to kind of highlight potential risky situations, but this is the type of thing that you have to test for and answer manually. Because again, for a scanning tool, it doesn't know if a directory, again, you might know that a directory called admin is sensitive. But what if your directory is called stuff, right? Is that sensitive or not? I don't know, scanning tool's not gonna know, right? So because this requires, or because this really asks questions about the business purpose of the application, the logic of this application, these are the types of things that you have to check for manually. And centralizing this type of authentication, authorization checking for access to different functions can have a lot of value because that allows you to keep this very sensitive code in a central known location so that it can be audited and reviewed. And again, this certainly applies to web applications, and what we're seeing more and more is this is a problem that is still cropping up, and cropping up with increasing frequency with thick client applications, mobile applications. It's a real problem for IoT applications when you got a whole bunch of little devices like trying to authenticate to different services and whatnot. And so from a threat modeling standpoint, this is a really important thing to pay attention to as you're looking at your systems and potentially doing threat modeling. And that'll hopefully identify places where you can go wrong so you can proactively address those. Yeah?
Just speaking from experience, don't try to engineer this in after you've built all your functionality. You have to do it up front. We had a mobile tracking IoT app that was receiving hundreds of messages per second or per minute. And because it was the whole pipeline of things that had to be done, one had roles and checks, we were literally getting like 4,000 database or ORM hits per second trying to do all of this authentication. Just don't try to bolt them on after the fact.
Yeah, and so just for folks who may not be able to hear that, this is something you have to do, or you really need to design it up front. You can't bolt on after the fact. Where if you have your system humming along doing what it's supposed to do, and he's talking about a system where the traffic levels were such that you couldn't after the fact add in a bunch of these checks. And I will say the most, we do, again, a lot of testing work, and we help organizations with a lot of remediation stuff. And the most expensive vulnerability that we've ever found and had to help someone fix was very much along these lines, where it was how does control get transferred from one system to another? And how do I authenticate, hey, this is a valid request that came to me from this other system? This organization did it wrong, and then promptly managed to connect to a couple hundred partners who also promptly did it the exact same way wrong, right? If you're in an organization trying to fix your own code, you know that that's a fight, right? They're like, hey, we did the security test, we need to fix these SQL injection and cross-site scriptings. Yeah, but we've also got these features that this hotshot VP promised to an important customer, and we probably want to do those first, right? Ever had those arguments? It's hard enough inside of your own organization to justify making security fixes. Imagine trying to get on the development calendar of a couple hundred other organizations because they have to change code that they've already built to link into your system in order to address this vulnerability. Again, well, I made a lot of money because of that, but I felt really bad for the guys that we were working with because they were in just a really horrible, untenable situation. And so, again, these are the types of vulnerabilities that can be really expensive to fix. If you look at fixing cross-site scripting, fixing a SQL injection, again, we've got some numbers on that. It's whatever, 16 minutes to fix reflected cross-site scripting, 9.6 minutes to fix reflected stored cross-site scripting or something. We've got some stats we've run on that. But then you look at this one vulnerability that was a change management initiative that got funded by the board, right? That like all of a sudden like it kind of skews the number. Like when you're doing stats, you kind of go like throw that outlier off the side to keep things squared away. So this is the type of thing that again, like very important to look at up front because again when you've got stuff connected in, you start getting a lot of traffic. Really hard to bolt on, and especially if because these questions of authentication and authorization often deal with the connectedness between systems. These are the types of mistakes that are really have the potential to be incredibly expensive to fix, which nobody likes. Nobody wants that, and that's not the way folks want to be spending their time. And so, to the degree that you can upfront use threat modeling to identify potential problems, and from a design standpoint, plan to have centralized places where you can audit your authentication and authorization implementation. Those are things that are going to serve you well going forward. Any questions about that? Fantastic.
Hopefully you guys are doing all right still. We're going to keep trucking along. I think we've got probably about an hour or so left here. We're on A8, cross-site request forgery. We've got 9 and 10. We probably won't cover any of the threat modeling stuff today. I've actually got 2 soccer teams I've got coached at 5 and 6 tonight. So I'm going to run out of here probably about 4 o'clock and take care of the kiddos. So let's keep rolling through. Cross-site request forgery. So this occurs when an application is susceptible to enforce background requests from users. The attacker uses a combination of cross-site scripting, which we talked about earlier, cross-site scripting, along with poorly implemented server-side functionality. And what happens is that cross-site scripting payload causes the authenticated user's browser to make an unintended request to an application. And then the server-side code sees that request. It looks like it's coming from the browser, even though the attacker's making them make the request, and they see the valid authentication credentials. So the server's going to say, hey, looks like a valid request, and it goes ahead and it implements whatever the request is asking for. The impact here is going to be moderate. I guess what happens is the attacker can trick the victim into performing some sort of a state-changing operation, or really any of the activities that victim is authorized to perform.
So some examples might be updating some account information. Maybe you want to change the contact phone number because that's what they use to validate when you call in. Or making a purchase. Maybe you're using their account in order to make a credit card purchase. Maybe it's logout functionality. And sometimes it's even something like account login, because you can use attacks like session fixation or something like that and log in as though you're that user. So here's a pictorial example here. We have our victim. The victim logs into their banking website just as they normally would, and then they happen to get distracted, navigate to some sort of a malicious website. When they hit that malicious website, there's a cross-site scripting vulnerability. And that cross-site scripting vulnerability basically says, hey, you're already authenticated with the site, go ahead and request to initiate this transfer of money from your banking site. And because that browser is already authenticated with that website, when they say, go ahead and make this request, the request comes from that browser that's already authenticated, therefore it sends the cookie along with it. It makes the request to the banking site says, hey, it looks valid, and it goes ahead and does the money transfer, whatever the request was for. And just like cross-site scripting, we have a couple of different variations of this. This can be stored or reflected, just like cross-site scripting, where it's either in the URL parameters or it's stored in the database. We can also use either GET or POST requests. So just because we're doing a post or something like that doesn't mean that you're completely out of it. So how would we test our applications for this? The first thing is we start from looking for cross-site scripting flaws. And we already talked about this. Cross-site scripting is easy to automate. It's a technical vulnerability or scanning tools. They send in a request, they get the response back. So they're really good at finding these things. Once we've found the cross-site scripting, then we look for the impact of these cross-site scripting flaws. So how much information can be put into there? Where does it get injected? Where are the domains that it gets injected into? And then we look for how the server-side functionality has been implemented. So the question is, can we make our cross-site scripting payloads that would exercise that type of functionality? And so to craft a cross-site request forgery payload, it looks just like cross-site scripting. We would start with our cross-site scripting payload. We deal with the pre and the post HTML like Dan talked about. And the most basic attacks are going to use GET requests. So it might be something like an image source where we're going to include in there, or a script, or a link tag, something like that. We can also use post requests though. So a post request, in this case, an XHR request, we can basically make that exercise the functionality and actually take multiple steps as part of our action. The biggest difference between these two is while GET is usually a pretty small payload, doing an XHR request usually involves a fair amount of JavaScript, and so it's going to be a much bigger payload. So mitigations for this, first, protect yourself against cross-site scripting. That means we positively validate our inputs, we do validation of the length, the type, the syntax, the business rules, whatnot. As Dan talked about earlier, the only way to truly get rid of our cross-site scripting vulnerabilities is to do HTML encoding on our outputs. So we want to make sure that we do that. Our less than characters become $LT, our greater than becomes $GT, and so on. And once we do that, we're treating the data as actual characters and not as code. The last bit here is designing sensitive server-side functionality with protection in mind. And so what this means is we're going to create scenarios where it makes it that much harder for the attacker to be able to pull off such an attack. And so things that we might want to do here is preferring post request to GET requests. Again, this is because it takes it's way easier to get a browser to make GET requests rather than post requests. Including random tokens with the request. This is called a nonce, or number used once. And we'll talk a little bit more about that in a bit. And then requiring re-authentication for sensitive transactions. This is part of the reason why if you're going to change the password, for example, it's going to ask you to provide your old password. Or if you're updating information in the system, a lot of times it'll be like, hey, let's get your password, let's validate you again before we update this information. In terms of post versus GET, like I said, it's going to be easier to force the browser to make a GET request versus a post request. You just recall the selection of the section. on crafting payloads. And there's lots of injectable tags that cause the browser to make these GET requests, which makes it really easy to do that. This can help to reduce the exposure, but it's not enough protection alone by itself. So we want to take a defense in depth approach. And as I mentioned, nonces or random tokens is the way to do this. So the whole idea behind a nonce is that we want to have either session or page specific random tokens that can pass in with our requests. And every time we load up a page, all of our form parameters, all of the values that are going to be coming is going to get this nonce. And that nonce is then validated when we submit the form to ensure that we are the ones who requested that form. And what this does is it makes it so that an attacker can't just go to the page. They would have to go to the page, and then they would have to get this nonce, and then they'd have to replay that nonce. So it's making that transaction much more complicated for them to do. We're basically ensuring that they aren't able to predict what that nonce is going to be because it's a random value. It's generated using good crypto, good randomly generated values on the server side, so secure random. We can do these a number of different ways. Finer grained tokens are going to be more secure but harder to maintain. What this means is, for example, I could have all my nonces with the name of nonce and some value, but at that point, I just have to look for nonce as the name, grab the value, and replay that. In this case, what I have up here is a nonce with a random name and a random value. This makes it much more difficult for an attacker to be able to guess what that parameter looks like, what it's called. They can't use JavaScript to just search for that thing. But it also makes it more difficult on our side to actually maintain that, to determine as our application what is and is not valid. The other thing to know about nonces is it'll actually break the back button in your browser because your browser expects you to basically doing a forward workflow. So you hit a page, it's going to give you the nonce, you submit the form that has that nonce built into it, you go to the next page. If you go back, you're going to get a different value for that nonce. And so that old parameter that you had in there, that old form token, is no longer valid. It's already been used. So it basically breaks that back button. And then requiring re-authentication. So making sensitive operations and multi-request process require the user to re-present their credentials. And the other piece that we can do here is we can use out-of-band facilities in order to confirm. So maybe it's an email or maybe it's a text message to basically reconfirm that they are who they say they are for those sensitive transactions. In terms of Java, it's basically what we talked about with cross-site scripting, where we're escaping special characters, HTML encoding our outputs, and whatnot. And this is where we start getting into the MySpace work that Dan mentioned earlier. So MySpace work was based on assembled JavaScript. It was built up from several different substrings. It bypassed numerous negative filters against malicious tags, attributes, things like this. And obviously this is on MySpace. Anybody ever heard of MySpace? Kidding. So it relied on the same functionality actually being served across multiple different host names. So they had profile.myspace.com and www.myspace.com. And it actually used a multi-step background combination of GETs and POST requests. So it's using both of those things. So the general idea of the MySpace form was this. Get the list of friends that a user has. Once you have that list of friends, parse out any special tokens, add Sammy Kampar, the guy who created this, as your new friend, and then you basically post the code for the MySpace form back onto that page. And so that means that anybody who visits that page is going to get that same JavaScript injected into their browser. When they get that JavaScript injected into their browser, they're going to do the same thing. They'll get the list of friends, they'll add Sammy as a friend, and they'll repost it. So what happens is it goes from first person who does it to every person who visits their page does it to every person who visits their page. And so it goes from this to that at the bottom, right? And so as we follow it kind of going through, I'll read this because it's kind of small. This is Sammy's recount of basically what had happened for the MySpace work. He says, if I can become their friend, if I can become their hero, then why can't their friends become my friend, my hero? I can propagate the program to their profile, can't I? If someone views my profile and gets this program added to their profile, That means anyone who views their profile also adds me as a friend and hero. And then anyone who edits those people's profiles adds me as a friend and hero. So if 5 people view my profile, that's 5 new friends. If 5 people view each of their profiles, that's 25 more new friends. And after that, well, that's when things get difficult. The math, I mean. So October 4th, 1234, he has 73 friends, not extremely popular. So he decides to release his popularity program. I'm going to be famous among my friends. 1 hour later, he has 73 friends and 1 friend request. He says, one of my friend's girlfriends looks at my profile, she's obviously checking me out. I approve her inadvertent friend request and go to bed grinning. Cool. 7 hours later, 8:35 a.m., 74 requests and 221 friend requests. Whoa, I didn't expect this much. I'm surprised it even worked. 200 people have been infected in 8 hours. That means I'll have 600 new friends added every day. Whoa. Right? 1 hour later at 9:30, he has 74 friends and 480 friend requests. Oh wait, it's exponential, isn't it? 1 hour later, 10:30, 518 friends and 561 friend requests. Oh crap, I'm getting messages from people pissed off that I'm their friend when they didn't tag me. I'm also getting emails saying, hey, how the hell did you get up to MySpace? Not that I mind you're hot. From guys, but more girls than guys. This actually isn't so bad. The girls part. 3 hours later, 2,503 friends, 6,373 friend requests. I'm canceling my account. This has gotten out of control. People are messaging me saying they reported me for hacking them due to my name being in their heroes list. Man, I rock. Back to my worries. People are also emailing me telling me their IM names, so I'll chat with them. Cool. Back to my worries. Apparently people are getting pissed because they delete me from their friends list, use someone else's page or even their own, and get reinfected immediately with me. I rule. I hope no one sues me. So then 5 hours later, 6:20, I timidly go to my profile, view the friends request, 2,503 friends, 917,084 friend requests. I refresh 3 seconds later, 918,268. Refresh 3 seconds later, 919,664. A few minutes later, I refresh 1,005,831. It's official. I'm popular. I've hit 1 million+ users in less than 20 hours. I've hit over 1/35 of all MySpace users. Every request is from a unique, living, and logging user. I refresh once more and now see nothing but a message that my profile is down for maintenance. I messed up, didn't I? I'm now more afraid and decide I'm never doing anything even near illegal ever again. To get my mind off of everything, I begin downloading a copy of the latest TikTok episode. An hour later, a friend tells me they can't see their profile, or anyone else's profile, or any bulletin boards, or any groups, or their friends' requests, or their friends. Nothing on MySpace works. Messages are everywhere stating that MySpace is down for maintenance, and that the entire MySpace crew is there working on it. I ponder whether I should drive over to their office and apologize. Another attempt to free my mind of worry, I go back to some episodes of the OC, which I downloaded a few days earlier, file sharing rocks. 2.5 hours later, I'm told that everything on MySpace seems to be working again. My girlfriend's profile, along with many others, still say Sammy is my hero. However, the actual self-propagating program is gone. I'm relieved that it's back up, as they can't claim damages for any downtime past this second if everything is in fact working properly. 10 minutes later, haven't heard from anyone at MySpace or Fox. A few minutes later, my girlfriend calls. I pick up and she says to me, "You're my hero." I don't actually get it until about 3 hours later. That's the MySpace forum. That's the kind of effect that these kind of things have. And so here's a picture from the MySpace forum in action. You can basically see the number of friends that he has. You can see all these people who inadvertently added him as their friend, all because of this JavaScript they put in there. So I use this as an example of what's possible because we can go from there into the lessons learned. What can we do better here? So the lesson is better input validation, right? What's that? Yeah, absolutely. It's changed a lot. And we've learned a lot of these lessons, right? Sammy learned his lesson, by the way. The feds came kicking in his door early in the morning, hauled him off to jail, and he wasn't allowed to touch a computer for a fairly significant amount of time. Super cool guy. He's been here to LASCON in the past. Really nice guy. He's still doing security stuff since then. In any case, so lessons learned. Better input validation, right? We talked a lot about positive versus negative validation. Obviously, we want to do positive validation wherever possible. This interpretable HTML is a really big place. So if we're trying to carve out, we don't want this tag or this bit or whatever, attackers are always going to find ways to work around that. The second thing is being careful about what functionality is available from where. Again, gets versus post, what applications are available from each of these different post names. And similar to checking to be sure that HTTPS content is not available via HTTP. The same kind of thing that we want to do there. So to recap, cross-site request forgery vulnerabilities allow attackers to force the user's browsers to undertake actions they don't want or even know about. We've got the same kind of varieties that we have with cross-site scripting. We've got stored and reflected. We have get and post. And to guard against it, we want to get rid of those pesky cross-site scripting vulnerabilities. We want to prefer our post to get because it makes it a little bit harder. And really the only way to get rid of this is to use random tokens. That's the only way to actually address the issue. Questions? No questions. Sammy's awesome. Oh, I'm sorry.
Just a quick question regarding the not. So if the attacker has an admin script on the client's browser, they understand the structure of the website that they want the request to go to eventually, could they do an AJAX call to that website, initiate a new form, get a new nonce, and embed that nonce in the they want the client to do?
So the question is, if the attacker has pre-knowledge of what that website looks like, and they have the cross-site scripting and the ability to inject scripts, couldn't they just grab the nonce and pull it out? It depends how that nonce is actually framed. If the nonce is framed in such a way where it's got this name and you know that that's going to be that name every single time, then sure, you could write your JavaScript that pulls that information and then grabs the value and then replays it in that way. But if you look at the example that I have up here, we're going to have to go back really far. Right there, you can see that the name is just a random number, right? And so if the name is a random number, there's no way for these guys to pull that. They might be able to traverse all hidden fields or something like that. But yeah, I mean, this is a value that's going to change. It's going to be unique to every page. It's going to be unique to the user session, perhaps. But it's not a value that they can anticipate in advance, which makes it that much more difficult for the attacker to actually attack using that. Yes, sir.
In this example, the user doesn't have control over how the servers run, but on the user side of the browser, there's certain plugins that are supposed to help how those work.
Do you have an example of the plugin? Yeah, Dan, are you familiar with browser plugins to prevent cross-site request
Some
forgery?
of the browsers have done things to avoid exploitation of obvious cross-site scripting. So
Yeah.
that might help. But I don't know of any C-specific browser.
Yeah, I'm not aware of anything specific to that either, but yeah, IE now has some built-in cross-site scripting prevention functionality, with Firefox and the same kind of stuff. So the browsers are getting smarter about that, especially in the case where it's injected through the URL, right? If you're doing parameter injection, reflected cross-site scripting, they're definitely getting smarter about that kind of thing. But I haven't seen any specific plugins with request to CSR. Anybody else? Okay. So let's move on to number 9.
All right. So using components with known vulnerabilities. Who here uses third-party components in your code? That's right, because otherwise no one would ever get anything done ever, right? Because everybody would still be writing their how to send email routine. So again, I forget the numbers, but if you look at the actual lines of code included in your application, you're actually probably only writing a tiny fraction of those lines of code. The rest of the code comes from other folks, vendor-provided frameworks, third-party license components, open source components as well. And so your application, you can do great work in your application, avoid introducing vulnerabilities, but if you, again, want to look at the security of the system as a whole, you also have to consider the security of the components that are compiled in and running parts of your application. And so these components, libraries that you're calling out to, frameworks that you're using to shape traffic to your application, software modules, like all of this is probably all running in the same process space with your code, with the same privileges that your code has. And so if a component has a vulnerability in it, and if your code actually connects to or calls into the code that has that vulnerability, the vulnerability in that component may end up being a vulnerability that's exposed and is remotely exploitable by people that are using your system. And like a challenge with this is really understanding the impact, because just because an application is using a vulnerable component doesn't necessarily mean that that application is also vulnerable, right? If the vulnerability is in a function and you never call that function, then it's probably not an issue. But you also have situations where if you're using like a vulnerable version of like the Struts or the Spring framework, any application that is including that component is automatically exposed and exploitable. And so that's one of the real challenges that we've seen working with organizations trying to get a handle on how they manage the security of components in their system is, again, with an application including a large number of components, especially if you haven't been making a very concerted effort to keep up to date with those components, you're going to have probably a number of components that have vulnerabilities that are included with your application. So if you run, the OWASP has a tool called Dependency Check, which is fantastic. There's some commercial offerings as well, so you can run tools and say, well, here's all the vulnerable components that you're including, and all the death and destruction that will occur if you ever turn your application on. It can be really challenging to go through and triage those results and determine, like, what do I actually want to fix? And I've talked to representatives from some of the vendors, and they say, well, from a hygiene standpoint, everybody should just keep up to date with all their stuff, so then you don't have a problem. I said, we're in the computer security space, how many people are exceptionally well versed in hygiene? And hygiene is a recommendation, it's not a requirement, right? In software security and in life. So again, it can be hard to justify, hey, we've got a vulnerable component. Do we want to go through the regression run after upgrading that component to find out if there's if there's an actual issue that was introduced by upgrading this component? So the impact here can be all over the map. Again, from, you're including 1 million vulnerable components, but you never call any of the methods that will expose that vulnerability, therefore you're not exposed. You don't actually have any additional risk because of those components, all the way to, just by having this component in your system, the way that framework works, that's going to give a remote user the ability to send in payloads or impact the behavior of the system. And so, again, that can be a real challenge when evaluating the risk associated with these vulnerable components. That makes it, again, candidly makes it hard, because if you're trying to make a justification, it's hard enough to, in a lot of cases I talked about, to convince folks to fix SQL injection, cross-site scripting, stuff that is very obviously exploitable. That challenge can be even greater if you're saying, well, we've got a vulnerable component, but I haven't gone through all the analysis to determine if we're actually exposed. So a wide range of impacts, and very dependent on your application, what your application is doing, how it's using the components, and so on and so forth. So you have to find out if you're vulnerable. What it usually requires is searching through vulnerability databases, like the CVE, the National Vulnerability Database, keeping track of project mailing lists and announcements for situations where there are vulnerabilities with the versions of components that you have. And then again, if one of the components in your applications does have a known vulnerability associated with it, you may need to do some impact analysis to figure out, are we actually calling into this code such that it's an issue. So component vulnerabilities can cause pretty much any type of risk imaginable, from really trivial stuff, sophisticated malware designed to target a specific component issue. All these components run with the full privilege of the application, so the impact is going to be tied to the privileges of what your application can do. But here's two good examples of components that were downloaded that the SonarQube folks have. They help run the Maven Central repository, so they've got great stats on like what components are being downloaded and how frequently. And so they've got really great data around that stuff. The Apache CXF component had an authentication bypass, and so you could manipulate the identity token and use that to access any web service with full permission, right? And that was just a problem with the framework in the way that it handled this unexpected scenario. Similarly with Spring, they had a remote code execution. You could manipulate the expression language that was fed to the Spring application, and that would allow attackers to execute arbitrary code, essentially allowing them to run code on the server. Any application that was including either of these vulnerable libraries is vulnerable to attack, because the way that these applications, or the way that these components behave as frameworks attached into like the request processing pipeline, that basically means if you're using these components, you're exposed. And so potentially really bad stuff.
Most of the libraries have it's hard to find just
Right.
so there are tooling that is in place in the Jenkins or Microsoft work and issues, but how do you know that you are like you said, that's the part. There needs to be, or is that just hard work of going on?
Yeah, so the question is, if you like, again, all these components have vulnerabilities. How do you find out if the ones? I think there's a commercial vendor. Like we'd actually talked to. We're doing some work with the Department of Homeland Security, some research funded by them, and we looked at potentially trying to like incorporate solving that problem, into the stuff that we were doing. And we haven't gone down that road. I think there's a commercial vendor that's looking at doing that to combine, kind of this component analysis with some static analysis, like essentially semantic analysis to identify, like, hey, I've got a known vulnerable component and the do stuff method is vulnerable. Can you tell me if we ever call the do stuff method? And so, right. Oh yeah, no, exactly. I mean, especially the languages that it's hard to do static analysis and stuff for, and JavaScript and Python and whatnot. But that's what the most interesting thing I've seen in that space, and I haven't been like super deep into it, but I do know there's one vendor that's combining that component analysis with the static, like semantic static analysis to identify you have a known vulnerable component. Here's the vulnerable method, and here's where you call it. And again, it's yeah. Exactly, and I think that like that it's been interesting to watch the progression. If you look at the way tool vendors work in the security space, like the static analysis vendors, to my perception for a long time are like, we find the mostest, right? If you look at this vendor versus this vendor versus this vendor, we find the mostest stuff. And then everybody like bought whatever would find the mostest and realized like I don't need the mostest, I need the things that like I can actually, like we're gonna find more stuff I can fix. I need to find the stuff that I actually need to fix, right? And similarly in my discussion, exactly, and similarly with this component lifecycle management vendors that I've talked to, they're like, oh, we're gonna find the most stuff, you need to fix it all. It's like, well, how many of your customers agree with that, right? And so then you see the customers deploy this, and it's like, well, I'll get some false positives out of the impact. I've got SQL injection, and so it's interesting to me to see that combination of static analysis with the component lifecycle management to potentially bring those together and be like, yes, this is here's 100 results, and here's the 5 you need to look at first. So it's that kind of I think as the tooling evolves, then we'll be able to identify not just the situations where you might be vulnerable, but the situations where you are more likely to be vulnerable.
What's your take on fusion? Is the best policy for shaming meaning any sort of component that has a let's go ahead and make it very or really show the exploits, or is it more behind the scenes, more like it's an open source?
Right, yeah. Right, yeah. So the strategies for if you find vulnerabilities in components, again, this is something where the CVE folks do maintain, like they do a pretty good job with the NVD and whatnot of maintaining a database of these things. And so if you find vulnerabilities in components at known versions, those are things you can get CVE numbers for, and then that gets that in that database, which then flows out to the tools to be identified. And so it's good that that data is starting to be available and available publicly. Yeah, there's not, I don't, you know, and some folks have been pushing for like a list, like an ingredient list. And I know there's a push to get like some legislation that says, hey, if you produce software, you also have to include an ingredient list of like, here's the components and the versions. So that at least if you're consuming software, if you're a government organization consuming software, you're guaranteed to get that, which that means it's available, you know, to private sector providers as well. Yeah, exact calorie count. Jeff Williams did some neat stuff looking at like nutrition labels for you know, for software, and I think you know, John Dixon's also looked at like food, like restaurant ratings and something like that. Right. Exactly. And so, like, this is a problem that this is of the entrants on the OWASP top 10. This entrant is a comparatively new. I think it only showed up at the 2013, and I think that it's just of organizations that I've worked with. It's the more advanced organizations that are taking this very seriously right now. It's the earlier adopters of the supply chain stuff, again, and the DHS folks have looked into that pretty extensively. And I mean, I was talking to Joe Drzambek, who's been here to speak at LASCON in the past, and he's like, you know, we're running software written by dudes that, like, I wouldn't let in the building if they showed up, but like, I'll run code that they wrote just because we don't know, you know, from a sourcing standpoint, we don't know. So that's, if you have a solution to that, you'll make $1 million at least. Good, so how do you prevent using components with known vulnerabilities? Like, and another challenge here is a lot of vulnerabilities in components get fixed silently. Like, some subset of them get turned over to MITRE, they get CVEs attached to them, and that's great. A lot of these components will silently fix vulnerabilities, and not necessarily like highlight themselves, like, oh, look at the stuff we screwed up. And so this is something where having a practice, especially if you have good application validation, like built in like a CI/CD pipeline, where you can make incremental changes, like saying, well, let's upgrade this component to the latest version and rerun all of our regression tests to see if we blew anything up. Like if your application is at that state, then that reduces the cost of you making these many small incremental changes, right? And that's kind of the thing with DevOps. Let's make a bunch of small changes, but let's make them very auditable so that we can identify, hey, this change broke something, let's go and maybe we'll roll it back or make a determination. So that's another argument to get yourself to a greater level of maturity, so that from an automation, from a speed standpoint, you can say, yeah, let's totally upgrade this one component, see if it breaks anything, and do that 50 times for all the components that need updates. If you can get to that level of maturity, in addition to the other benefits that brings, that allows you to be a lot more nimble with these type of upgrades. These type of upgrades, and so it reduces the cost of you staying closer to the cutting edge from a release standpoint. So how do you prevent using components? You need to have an ability to go in and identify the components that you're using, including the dependencies. So if you're using a build system like a Maven or something like that, Maven's great for being able to say, well, here's all the components, and for each of these components, here's the thing that they rely on. This is the type of thing where with a tool like Dependency Check, or with some of the commercial tools along those lines, you have the ability to monitor the security of components based on these public data sets. And then you need to have in your organization some sort of policies in place about what components you're allowed to use. Again, this is something where we see a wide range of variability from organizations where they say every open source library that we use has to have a sponsor who is responsible for keeping track of the version and whatnot. And that's on the very restrictive side, all the way to we're not paying attention to the stuff that we're using, so who knows what's in our code. And so again, if your organization has a better idea of what's acceptable for using components and what the vetting process is for new components, that again can help give you better situational awareness, albeit with a cost of slower development time and potential less agility with the stuff that you're using. And something that we've also done in certain cases, and we've done this more looking at making calls into native libraries from a managed language like a Java or a .NET. But you may also want to consider adding a security wrapper around certain components in order to disable functionality you don't want to have available, or to shape the inputs that are allowed to come in. And that's something that we've seen folks do in a .NET environment where you may be wrapping old DLLs and stuff like that are running native code. Same thing if you're using like JNI to call native code from Java. That can be something you can do to say, I don't know, and there was a great example earlier, like the whatever pay something library. Who was talking about that? The payment gateway library that had like a SQL injection vulnerability in it. In a case like that, you could potentially wrap that component and say, I'm going to do my own input validation or encoding in order to work around the problem that this library has. So these known vulnerable component problems crop up when your application is using components that have known security vulnerabilities. And this can have a wide range of impacts from undermining your application defenses, enabling a range of attacks. And again, a very large challenge with this is to do that impact analysis. We are using a vulnerable component. Does that automatically mean that I'm exposed to problems that I need to panic? Or does that mean that I need to spend some time looking to see, are we actually using the functions in this component that are vulnerable, and are we doing them in such a way that that you're exposed to issues? And again, this is something where you need to have a process in place to identify the components in your application, to identify the versions that you're using, and to compare those against known vulnerabilities in these components, so that you can make a risk-based decision to upgrade or not upgrade based on the information that you've collected about this stuff. Any questions about known vulnerable components? All right, home stretch.
All right. So, this is the OWASP top 10. This is OWASP LASCON. I figured it's probably only fitting that I say a word or two about what OWASP is. OWASP is the Open Web Application Security Project. The whole goal of OWASP is a 501c3 not-for-profit organization, global organization, and the whole goal is to make application security visible and to give you guys tools and processes, policies that you can use in your AppSec programs to make your organization more secure. And so Dan's actually done a really good job highlighting a number of tools as we've gone through. I know he mentioned OWASP Zap a couple of times, great proxy tool, good for finding vulnerabilities and things like that, web testing. And then in this last section, he mentioned OWASP dependency check as well, another great tool. But those are, between those and the OWASP top 10, that's this much of OWASP and what all is there. OWASP top 10 is probably the most visible project at OWASP because there's lots of different standards like PCI that actually references it directly, but there's lots of stuff there. So, it's kind of cool. There's a OWASP game, and so if you want to do, I forget what it's called, but if you want to do threat modeling with your developers, there's a game for that. The same guy did an OWASP Chutes and Ladders game. There's just all this stuff, and so fantastic organization. Everybody, you're all welcome if you'd like to participate. If you have an idea for a project that you want to get started on, OWASP has some fantastic resources. They've got money and people and whatnot to help with those kind of things, and it's all about getting this stuff out there, getting it into the community. So I wouldn't be doing my job as an OWASP board member if I wasn't kind of pitching OWASP and telling you guys what it's all about. So really hope that you'll take the opportunity, if you're not already involved with the OWASP Foundation, attending our local chapter meetings and things like that, take the opportunity to get involved. So now we're on to the last one, A10, unvalidated redirects and forwards. We'll talk through this a little bit, and then there's a couple others at the very end of this presentation that we probably will be able to cover briefly, and then we'll quit for the day. I know it's a lot of information that you guys have been consuming, and you'll probably go home and take a nap after this. I wish I could if it weren't for the soccer games. So I'm exhausted. But I guess, what is this guy? Applications will frequently redirect users to other pages, or they'll use some sort of internal forward in a similar manner. And so sometimes that target page is actually specified in a parameter. So, it might be something in the URL, redirect equals, or URL equals, something like that. And if it's specified in that parameter, and we don't do any validation on that, anything like that, there's potential for the attacker to be able to specify their own URL and choose where that user is going to go to. And then the attacker can link to that unvalidated redirect and trick a victim into clicking it. And victims are more likely to click on it because it's a link to a valid site. So the attacker basically targets this unsafe forward, either trick the user into going someplace else, or in some cases, there are security checks that actually get bypassed based on this functionality. I'll give you an example. A lot of times you'll see this with like login pages, where you'll go to a login page and you go because you click on a link, and it'll take you to the page where you log in, you enter your username and password. When you hit go, it'll authenticate you, and then it'll look at that parameter that got passed in via the URL, and that parameter is the page that's going to redirect you to after it authenticates. And so, unless the application actually validates that URL parameter and says, is this part of my application? Is this a known domain that I'm supposed to go to? If it just allows it to go anywhere, then there's potential for the attacker to basically piggyback on the fact that you're going to trust that domain, www.ni.com or OWASP.org. It piggybacks on the fact that you trust that domain in order to send you to a domain that you probably shouldn't be trusting. You probably wouldn't if you didn't know better. So the impact here is going to be moderate. These redirects may attempt to install malware. They may trick the victims into disclosing passwords or other sensitive information. Sometimes they can allow you to bypass different access control mechanisms. So what we want to do here is consider the business value of retaining our users' trust. Because ultimately, this is more along the lines of cross-site scripting. It's not like this is going to result in the full compromise of your server or your network or anything like that, but they're leveraging the trust that you have in those domains in order to basically turn you into a victim, take over your browser and things like that. So, am I vulnerable? Well, how do we figure that out? The first thing we want to do is review our code. And we look through our code and we want to see if there's any sort of redirects that are in there. And so a lot of times this will manifest in like a location header. So you'll see towards the beginning of the file before any content is written to the page, you'll see like header, location, colon, and then whatever that parameter is. And so that's what tells the browser, hey, go ahead and redirect to this other page. And so if you see that, you look at the target URL that's included in there, and you say, does this parameter, is this validated in some way to only contain an allowed destination, or the element of the destination? Maybe it's a particular page or something like that. And if it's not, if there's no validation there, then there's nothing to prevent the attacker from redirecting them to something like evil.com. Also, what we can do is we can spider the site. And when we spider the site, we want to look for any pages where the response code is going to be in the 300 range, usually a 302. 302 is basically it tells the browser that this page has been moved somewhere else. So it's another form of a redirect. We look at the parameters that are supplied prior to that redirect, and we see if they appear to be a URL. So if there's a URL or something like that, a piece of the URL, maybe a page name, then we want to change that URL and see if the site takes us someplace else. And if it does, then we may have this issue. And then the last one here is if we don't have the code, the code's not available to us, then we want to check all the different parameters to see if they look like part of a redirect or a forward URL destination and test those that do. So we're just looking at the URL parameters and we're seeing maybe there's a URL equals parameter. That sounds suspicious. Maybe there's like a FWD equals or something like that, target equals. We want to look for those kind of things, change the data, change the parameter that's pointing to, and see if it does something different in those cases. Yeah, you got it. So the question is, is there guidance on what types of redirects to use? Yeah, I mean, I think there's different types of redirects that you would use in different situations. For example, I mentioned the location header redirect. That's something I use a little bit in my SimForce application, but you can only use that in the header. So you have to use it before any code is called, which means that if you display some function on the page, or if the redirect happens as part of like a click this button or whatever, if that's what triggers the redirect, then you can't use that. You have to use something like JavaScript and do a JavaScript redirect for another page or something like that. So I think a lot of the different types of redirects is more about what scenario you're trying to use that redirect under, not necessarily which is more or less secure. Really, the more or less secure part comes in terms of where it's redirecting to and how that parameter gets stuck into there. So if you're using a location directive, for example, and that location comes from a parameter that's being passed in the URL, then that's probably an unvalidated redirect unless you actually do your validation. Right? That makes sense? Cool. No problem. All right, so let's look at a couple scenarios here. The first one, our application has a page that's called redirect.jsp. Nothing suspicious about that, right? This takes a single parameter named URL. Okay. We have a page called redirect.jsp with a URL equals parameter. That sounds like potential there, right? So the attacker then crafts their malicious URL that redirects users to a malicious site that performs phishing and install malware. So in this case, you can see what that would look like. In this case, we have www.example.com. And most people, when they see something like that, they're not going to look at all that stuff on the end. They're not going to see the URL equals evil.com. And chances are actually pretty good that that URL equals evil.com won't even show up in the browser window, right? You'll see this much of the URL, say www.example.com. It'll have their SSL certificate, it's HTTPS, things like that. And then all of a sudden, they'll be redirected to this other page where it's going to be installing malware and things like that. So very, very hard to detect. It can be even worse with link shorteners. I gave you guys a bit.ly earlier. How many of you guys wrote that down and were going to trust that I'm sending you to the right place, right? Yeah, I mean, there's nothing stopping me from throwing one of these guys in there or really just sending you directly to the evil.com site. But the fact is that pretty much everybody trusts those bit.ly sites, right? There's nothing. We'll go home, we'll plug that into the browser, no problem. But that's doing the same kind of thing. It's doing a redirect, sending us to some other page that I've effectively stored on their server. So hard as a security professional to trust that kind of thing. Second scenario here, we have an application that uses forward to route requests between different parts of the site. And in order to facilitate this, some of our pages use a parameter to indicate where the user should be sent if a transaction is successful. So in this case, the attacker crafts a URL that will pass the application's access control check, and then forwards the attacker to an administrator function that they would not normally be able to access. So you see this example.com, mooring.jsp, and our forward equals admin.jsp. So we're leveraging the fact that this application trusts the parameter that's being sent here, this forward parameter. It does the validation, but it doesn't validate where it's going to. So it just assumes that I should have access to that, and it sends me to that page. So how do I prevent this? Well, the safe use of redirects and forwards can be done in a few different ways. The first is you avoid doing it, right? If you have any choice at all, and you can get around the fact that you're using some sort of redirect or forward, just don't do it. The second one is if you have to use a redirect or forward, don't involve parameters in calculating the destination. So that means taking user input from the URL request parameters. If you do that, you're just inviting trouble, right? Because now you're probably getting into this neighborhood of positive versus negative validation. How do we make sure that's the right thing and all this stuff? So if we don't have to involve parameters from the user and we're just specifying location equals, and if this action happens, then we have to send it here, and it's hard-coded into our application, usually we'll be pretty good. It's when we start taking those URL parameters and feeding those into our redirects, that's usually when we get into trouble. And then the third one is if we absolutely can't avoid it, if we have to take those requests from the user, maybe like that login thing where we'll redirect them to a certain page after login, then we need to ensure that the supplied value is valid and that's authorized for the user. So we want to make sure when we go through and we do whatever input validation we have on that, that's going to the right domain, everything is appropriate for that, and that this page that I'm going to send them to is the right page that they should have access to. And it's recommended that any such destination parameters be a mapping value rather than the actual URL or portion of the URL. So in other words, instead of saying, like in this example, forward equals admin.ksp, it would be forward equals 1 or ABC or whatever the case may be, and then we would map that back to this value equals this parameter. What that does is it means that we only have a very finite definition of these are the possible values for our application. We're kind of doing like an ORM type of mapping, and if it's one of these values, if it's this value, then we go here. If it's this value, then we go here. If it's not one of those values, we don't do anything. So we're basically doing this positive validation using those parameters. That's right, server-side redirection, absolutely. All right. So the other thing, we haven't talked much about this, but OWASP has something called the Enterprise Security API, or a SAPI. A SAPI is something it's been around for a while. Primarily Java. They do have versions. I think there's a C or C++ version. There's an ASP version. I think there may even be a PHP version. I don't know how well those are supported. I probably wouldn't recommend just going ahead and baking the ES API into your application. But at any point in time, if you're trying to find a way to implement a certain thing, maybe it's how do I do this crypto call in Java, or how do I do some sort of mapping of the database or whatever, a SAPI is a great place to go and look for that. I believe it's up on Google Code. You can go, you can search it for certain functions, and then you can look and say, oh, this is how they implemented that, and then use that as a kind of a development archetype in your own code. So in this case, SAPI has something called send redirect. It's a method that they wrote into SAPI to make sure that redirect destinations are safe. So we can use something like that in our code. Avoiding these flaws, obviously, is really important because they're a favorite target of phishers trying to gain the user's trust. They're counting on the person to see that domain, to see www.owasp.org and say, yes, that's something I'm trusting. I'm willing to click on that link because I trust OWASP that they're going to keep me safe. And then if we have that unvalidated redirect that redirects them to evil.com, all of a sudden the phisher is able to get their credentials or load malware onto their system because they're abusing that trust. Questions about that? All right. So recap, this happens when an application redirects a user to another page using an unvalidated parameter. It utilizes a familiar URL to trick the user and bypass security checks potentially. Once they do that, they install malware, trick the user into disclosing passwords or other sensitive information. When I do this training for my developers, I actually use an unvalidated redirect, and I just forward it over to a ni.com login page. And it looks like ni.com, smells like ni.com, and as soon as I enter username and password, it captures that information and then redirects them back to the actual ni.com login page. Uses the ni.com URL, everything, so they would trust it. And then when they log in again, it logs them right back in. So it looks like it's just a fat finger or a typo, when in fact I capture their credentials on the first entry. So you can definitely use that. To find this, we want to check for those unvalidated parameters in the redirect code, and to prevent, we need to validate our redirect parameters. So references, there's an OWASP article on open redirects that's good, and then I mentioned the send redirect method for SAPI. So that's our OWASP top 10 security risks. Questions about that? Should we start over and go through it all again? We are recording the video, so if you guys want to go back, you guys want to learn more about something like that, you guys are welcome to do that. We can probably go quickly through these other prominent security issues. There's not a ton there, but they are good things to know. The first one is buffer overflows. This is not something that you're going to see in your standard website, right? This is typically something that you're going to see in things written in C or C++. The idea is that you have a fixed size buffer that the application allocates, and then you have content that goes into that buffer that goes longer than the buffer length. And by going longer than the length that we've allocated for the buffer, it allows us to write malicious code over other places in memory that we haven't allocated. So here's an example. This kind of shows what it looks like. In this case, the picture on top is how much memory we've allocated for that buffer. The next one is in ideal scenario, we would have data that would go into that buffer, and that data would be less than or equal to the size of that buffer. But in the third picture, what we see is somebody's taken some malicious code, they've overwritten that buffer, and you can see how it goes outside the size of the buffer and actually starts writing into other areas of memory. And so this is a way that the attacker can actually get your system to run their code, and once that happens, it's game over. Your system belongs to them. This is a lot of the big vulnerabilities like the MSO 8067 and stuff like that. The big vulnerabilities they use for remote code exploitation or remote system exploitation, they're usually something like this, a buffer overflow. Here's an example of some code with a buffer overflow. In this case, we've defined a buffer. It's a name buffer. It's of size 10 characters. We then say enter the name, and then we get that information back. Get s is get string, so we've taken that input. And what happens is, because we've only allocated a 10-character buffer, if we put more than 10 characters into there, we've now started going outside of that initial buffer. So this is written in C. To make this more secure, they actually created a new function called fgetx. So it's basically a secure version of getString. And with this now, what we specify is not only the name and the input method, we're also specifying the size of the data that we expect. And so if it goes more than that size, then it's not going to allow us to allocate that beyond that to that buffer. So it limits the size of the input that's allowed to only the size that we specify. By careful manipulation of the payload, the malicious user can control the instruction pointer. That's the piece that basically points to the next instruction that your CPU is going to run. And then once you are able to modify what that next instruction is, you basically are able to run your own code. And even with less sophisticated payloads, ones that don't necessarily say, here's your next instruction to run, you can usually overwrite it with garbage data. And as soon as you overwrite it with garbage data, you're basically creating a denial of service attack. It means that that instruction pointer is going to move on to garbage, and then it's going to start running garbage, and your system's basically going to crash. So mitigations for this, like I said, most of our development environments don't have to fear from this guy. It's not going to be an issue unless we're doing something like C or C++. That's where you're going to start to see this kind of thing. So in those cases, we want to use safe array and string handling routines so that our buffers are being allocated and we're checking the size of our input before it sticks in there. The other thing we want to do... Siri wants me to repeat what I said. All right. The other thing we can do is for any COM objects or other potentially unsafe code, we can wrap those in wrappers that will enforce proper input validation and cleansing before it gets passed to the vulnerable service. So that kind of leads us into denial of service, which the whole idea here is that we really just want to watch out for situations where an attacker can use a lot of your resources with minimum commitment of theirs. And I'll use an example from my environment for this. We had an application where if you did a certain thing, took a certain action within the system, it allocated about 300 megabytes of memory. And then if you kept that browser tab open, went into a new one and did the same thing, it would allocate about 300 megs of memory. Well, you can imagine like how many browser tabs you would have to open, and you're now into the gigs of memory. Most systems these days, you're looking at 32, 64 gigs of memory. If you're lucky, it's going to be 128 or something like that. Probably not much more than that. So it really doesn't take that much of that attacker's resources to tie up all that memory. And now all of a sudden, nobody else can use that system. The system is basically crashing. So things that we want to watch for, areas where you use memory, areas where you use CPU, places where you do like logging routines, mostly because of the hashing and the complex algorithms that we talked about earlier. XML processing, you can do some DOM injection. There was a cool talk that I saw when I was in Costa Rica to the OWASP chapter there, where it was talking about recursive XML, and basically you create a DOS condition through the XML process. It's really interesting. And then logging routines, so places where we're going to write a lot of data to disk or something like that. And then the last one here, information leakage and improper error handling. So this occurs, Dan kind of talked through this in a few of the different scenarios. It occurs when our application provides too much information to the attackers. So this might be a result from failing to trap error conditions. So you have things like exception stack traces, you get file paths and whatnot. Or it could be the result of verbose application messages that provide attackers with information they shouldn't have. And so Dan mentioned invalid username, invalid password, both of those kind of exposing what the scenario is that the application had before it failed. So we want to go with something a little bit more generic, like invalid username or password or error, because that doesn't give the attacker anything that they can use. Impact here, the attacker learns about the internals of the system, and then they can use that information to wage additional attacks on their system. Maybe a direct attack against the system. Maybe it's just that now they have enough information about your environment based on the stack dump that had system name in it, and application name, and a lot of technologies and things like that, where now they feel comfortable calling your service desk and saying, hey, I was on this system called whatever, and I noticed that it had this application that gave me this message or whatever, and they can use that to social engineer those people. Unhandled exceptions sent back to the browser. They can contain exception messages, stack traces, file names, other information. This is all information that they can then use for that social engineering. Application provides a reasoning or justification for a given. We're going to talk about that. The attacker then can use that information for brute force. So how do we test this? The way that we test this is we send unexpected inputs to a system, and we look for system error messages. And this is called fuzzing. We talked earlier about ZAP, the lost Z attack proxy. ZAP has built-in fuzzing abilities, and so these type of attack tools are actually really good at this. If it's supposed to be field equals something, then the server will see an empty string. If it's empty, then the server will see null. If it expects numbers, then we should send strings and special characters. We're basically giving the application data it never expected, and then looking at the results that come back, seeing if there's something weird that happens. So don't allow the users to see verbose error messages. Be careful with logging error conditions. And be careful what information we provide to others. Logging error conditions, it's important for security operations personnel. Obviously, if I have an error message, it allows me to debug the problem. It might be something where if there's an attacker or something like that, the error message will allow me to do some sort of intrusion detection, research, forensics, that kind of thing. So having that information is good. The problem is when we're logging into files and things like that, we have to be wary of ways that the attacker could have used that. So one example is if an attacker can send an end of file character, and that information, that end of file character gets sent to the logs. Anytime you view that log, your editor is basically going to view it up until it sees the end of file character. And then everything after that character, the editor isn't going to show, even though there's lots of data after that. So this might be a way that an attacker would basically obfuscate their activities on the system just by inserting that end of file character into the log file. The other thing here, based on the DOS stuff that we said before, don't make logging an expensive operation. Obviously, denial of service concerns. I had a situation where we were running an app scan against an environment, and basically every time it got a 404, it would submit a form that then sent an email to our system. And so when the person woke up the next morning, they had 10,000 emails, and they weren't very happy with us. So be really careful in those kind of situations. It's a DOS, but it's a DOS of that person, and it makes them not really willing to work with us in the future. So we want to be careful with that. What we should consider is we should consider logging errors to a database, give them a unique identifier, provide that unique identifier to the user. We can give them a message that says, an error occurred, if this persists, contact support, here's a reference number. That reference number is random, they're not going to know what that means, but from a support side, from a debugging side, we can then go, we can look up that value, and we can find the actual error message that was associated with it. So it gives us enough information to troubleshoot, but it doesn't give the attacker any information that they can use to wage any further attacks on us. And obviously, we talked a little bit about social engineering. There will probably be a lot more at LASCON talking about social engineering and whatnot. But anybody who communicates with users should really be aware of social engineering attacks. This means service desk people especially, but really anybody who's getting on the phone and talking to people. There's always a chance that somebody could be telling you something because it's what you want to hear, and it's what they need in order to get you to do something on their behalf. So with that, that's the end of the presentation here. We're basically right on time. I got to run, but I'm guessing, Dan, you're going to stick around for a little bit. So if you guys have questions, feel free to talk to Dan. And I really hope that we get to see you guys at LASCON tomorrow. Thank you.